Hi, we're Team CS063, and this is Watch Your Sleep, a smart alarm for optimal wakefulness, built natively for iPhone and Apple Watch. I'm Sahith Chandra, working on the iOS UI and alarm configuration. You'll hear from Carson Seacrest on the watch side and Rahul Vikram on alarm infrastructure. Let me walk you through the problem we set out to solve. So, for the next minute, let's talk about what's broken about how we wake up, who's paying for it, and the specific slice of that problem our team took on to solve. So, traditional alarms fire at a fixed clock time. The clock doesn't care what your body is doing. If the alarm goes off while you're in deep sleep, the wake up is abrupt, and you spend the next hour paying for it. That's called sleep inertia, grogginess, lower focus, and reduced productivity throughout the morning. So who pays that cost? Pretty much anyone who uses an alarm. It hits hardest on health conscious users already tracking sleep on Apple Health, and on shift workers and even students whose schedules are already irregular. A foggy first hour sounds minor, but compound it across a week and it's real lost time. So, why hasn't this already been solved? Existing trackers like Sleep Cycle or Apple Health report your sleep stages, but they don't act on them. HealthKit specifically doesn't expose sleep stages in real time. You'll only see them after the fact. An alarm kit, the Apple framework you'd usually use to trigger a critical alarm, shipped only 1 month before our project started. So these sparse docs and undocumented edge cases meant that building something reliable had us trying to figure it out, most of it from scratch. Our specific scope was a native iOS and watchOS app, classifying sleep stages locally on the watch using core motion and heart rate, then triggering an alarm inside a user-defined wake window via AlarmKit. Explicitly not in scope was Android, Fitbit, Garmin, medical diagnosis, or LLM-based prediction. We kept it tight on purpose. Carson, take it from here.
All right, so now on to the actual live demo. So for the phone, I've recorded this video on my actual phone so you can see how it's working. So first we're just gonna sign in. All the sign-ins done through Apple, so we're keeping everything just mainly through Apple here. Here's our main screen. You can see our number of nights we have calibrate at the top. I just tapped on it and you can see 3 out of 3 completed with a little note. Let's go ahead and add an alarm here. Here's where we can add an alarm. You might recognize this if you use the normal alarm app. We're setting one for 10 a.m. Then we're gonna adjust that wake window there so you can wake. You see a little message, your alarm will ring earliest at 9:30. That means that our wake window, so let's say we detect core sleep, it can wake us up at earliest 30 minutes before our actual alarm. Here I'm just deleting it. I was just showcasing our alarm functionality. And now the second part, I'm going over to the metrics page. Here's one of our views where we can show all the data. So here we have, that's my heart rate. You can see average, low, high, other stuff from my heart rate in this one night. And then here's some motion from one of the nights that I record. This is all real data, by the way. Over on the insight screen, we can see how long we slept, when we started and ended. And here are the different sleep stages, which we're using to make our predictions. So you can see core to deep to REM. And then sometimes we awake. This looks exactly like the Apple one. And then here are some insights we were also showing as well. Here we can actually switch the date. So we're graying out all the dates we haven't slept, but the white ones are where we have slept. I just picked the one that looks, I guess, like the most appealing for this demo. So yeah. And now I'm going to show you this little profile. So here we have our profile view with auth, some privacy support, and also sign out. And here I'm going to turn on the developer pages. And so now we can actually have this developer view. So we can see our thresholds and that we can reset the sleep profile here. And then on the insight screen, we actually have this demo. So this demo here, we're simulating, let's say you set an alarm for 7 a.m. with a wake window of 10 minutes. You can wake up at earliest at 6:50. And it's just speed running through it. So from 6 a.m. to 7 a.m., every minute here is actually a second. So you can see 30 minutes is going by quick. But this is basically meant to simulate the end of your sleep. So, or like right before the alarm triggers. So here you can see we're detecting sleep, REM, and core. And then there, right when we get into that final 10 minutes right there. So we had core, and when we hit that wake window, it actually woke us up. Everything in the simulation is actually completely real. So it's based off of one of my actual nights of sleep. So we just loaded a massive CSV there that was actually recording at 50 hertz. So that's a lot of data points there. And it's actually going through our real smart alarm or our real classifier engine in this demo. Here I'm running it again so you can just see. So it's actively classifying this real data as sleep. It's jumping around because we're actually smoothing it out. Otherwise, it'd be going up and down a lot more. But yeah, we're just like basically smoothing out the data here, making sure that it's predicted right. And so here, yep, and then it starts predicting core. But then it realized, oh no, actually it all fell into REM. But then here we can see we get into this 45. We're right before that 6:50 window, and then we're in core sleep, and it wakes us up. So yeah, yeah, that's our mobile app, and that's our demo of real data with a real classifier. Now on to the watch. And here we have the actual Apple Watch app. So here we have this ready for bed. So you can just start your sleep session here. First has to actually connect to HealthKit in the phone, but then, whoops, it was already doing it. There we go. And so now it's in an active sleep session. So it's tracking, motion, heart rate, and sending this data to the core data in iPhone. Yeah, and then here we can just wake up whenever, let's say like we want to end it automatically, like if it didn't trigger. But yeah, this is where all of the actual recording of the metrics that we're using in the classifier are actually recorded. So yeah. So yeah, now a quick look at to how all that's wired. So on the left here, the watch runs a sensor pipeline at 50 hertz, feeding both the local storage and a sleep classifier here. The classifier reads thresholds from a sleep profile object. When it detects light sleep inside the wake window, it triggers the alarm kit locally on the watch. Separately on the right, the iPhone runs scheduling, so triggers these alarms. It also runs the dashboards I just showed, sign in, and calibration engine. This calibration engine is what recomputes the watch's thresholds from historical data each morning. Three decisions over on the right that actually matter the most. So one is on watch detection. Sleep stages get classified locally, so the alarm fires even if the phone is dead or out of range. Two is the WC session sync, so configs go phone to watch, so bulk CSV exports go watch to phone for the next day's calibration. And then three is alarm kit plus a user notifications fallback. So alarm kit gives us critical alerts that bypass do not disturb, which a regular notification can't do. But because this alarm kit actually only came out this last year in WWC 26, it's kind of unstable. So we kept the older API as a safety net as well. A couple things this architecture does give us is on the left we have the heart rate stability by sleep stage from a spike we test ran in Sprint 4. In the middle box is deep sleep with a very tight heart rate variance, standard deviation just under 1 beats per minute. And REM is on the right, it's wide open, sometimes over 4 for the standard deviation. That separation right here is what gives us, or what makes the classifier even possible. Without that signal, all the stages look close to the same in the motion only data. On the right here, what the actual raw export looks like. So each row is a 20 millisecond sample, not here exactly. These timestamps in reality would just all be about 214 because it'd be 50 per second. But here we have the timestamp, accelerometer magnitude, heart rate, and the classified stage. At 50 hertz over an 8-hour night, that's about 1.4 million rows per sleep session. That's a lot of data, and early on it was a real memory risk. We added a 7-day retention policy and page fetches in the calibration manager to keep it bounded. So yeah, now it's on to Raul for what we actually shipped.
So for outcomes for this project, first, what we delivered, we shipped a native watchOS and iOS sleep tracking app end-to-end with sleep history and smart alarms on dashboards. And these alarms are backed by Alarm Kit with live activity, which shows the alarm on the dynamic island. We've also made a native Apple sign-in mechanism through Keychain and published our app to test flight. A couple of the things we partially delivered are like performance metrics and things we planned but haven't yet started development on, like customizable sounds and calibration outlier rejection. What we explicitly said we're not doing is Android or other wearable device support besides Apple stuff. We're not doing any AI or medical grade diagnostics and prediction, and we're also not deploying anything beyond test flight. And what's proven is that Test flight deployment has been reached and it's a usable beta in real users' hands. Our targets were 90% wake window accuracy, 85% sleep stage classification accuracy, and 80% user reported reduced grogginess. Our system built can answer these questions through our technologies, but we just don't have enough test data from users doing our beta testing yet to claim that we've actually proven these thresholds. But what we have shown is that heart rate stability is the definite separator between deep sleep and REM sleep, and this was proven through a spike test in Sprint 4. And for lessons and what's coming next, we learned to prototype our API first. So, because mid project, we learned that HealthKit doesn't expose any sleep stage classifiers, so we had to build our own using lifetime data. We learned to design for degraded states. So, our watch, when it was dying during sleep tracking in the night, our CSV export pipeline was breaking, which means calibration was never re triggered. This relates to the CAP theorem in distributed systems where we had to prioritize availability by introducing an offline fallback. And then feeding AI tools fresh docs is super important because AlarmKit came out a month before we started our project, and AI models had little to no knowledge of what the code actually was or the documentation was, so it would hallucinate a lot. So what we had to do was manually feed in documentation to AI models before interacting with them. And we also have a list of next steps that we're planning to do. That's it. Thank you.